Okay. So last time, if you recall, we studied characteristic polynomial of a linear map. And so today we'll see how it helps. Yeah. So we'll also study something called minimal polynomial. So I'm not sure whether we'll get to minimal polynomial today, but we'll study some how characteristic polynomial helps us understand the linear map. Yeah. So for instance, certain properties of characteristic polynomial will tell us whether whether the matrix associated to the linear map is similar to an upper triangular matrix or not, and so on. Yeah, so triangulable, or whether it is whether. So sometimes you can also decide using the just looking at the characteristic polynomial whether the matrix is diagonalizable, and so it doesn't decide completely, but sometimes it can tell you whether it's diagonalizable. Okay, but minimal polynomial together with characteristic polynomial more or less determines whether the linear map is diagonalizable or not. Um, or doesn't, but it gives you better understanding. Yeah. So let's start with uh, we used so this endomorph. So let me fix one more terminology. So if we start with an endomorphism of a vector space over a field F, then phi is also called a linear operator on V. Yeah. So many books use, and those who work on Hilbert space higher dimensional linear maps endomorphisms on higher dimensional infinite dimensional vector space like Hilbert space and stuff, they usually use the word operator. Okay. And those who work in some more algebraic area, they use the word endomorphism. So remember the eigenvalues of the, so last time we saw that eigenvalues of phi are the roots of the characteristic polynomial, which is which you can define it as determinant of Ti minus phi. Yeah. So and this does not depend upon the choice of the basis. That also we saw. Yeah. So in particular, as a consequence, we get that if phi is a linear operator on a n-dimensional vector space, and then phi can have at most n eigenvalues. Yeah, because they have to be root of a degree n polynomial. Yeah, so you can't have more than n roots of a degree n polynomial. So it can have at most n eigenvalues. And if the field F is algebraically closed, then we know that it has at least one eigenvalue. Yeah. Can it have n eigenvalues? What happens if F is algebraically closed? What can you say about the characteristic polynomial? How does it look? So you know what algebraically closed field are? Yeah. So how will the characteristic polynomial look if F is algebraically closed? Like for instance, complex numbers. So you can find one root, but can you find n roots? Yeah, so what does it say? So it says that the characteristic polynomial is product of linear factors, right? 1 second. Okay. So we can say that the characteristic polynomial is product of linear factors, right? Because that is what any polynomial, in fact, is product of linear factors over any non-constant polynomial over an algebraically closed field is a product of linear factors, right? Because any polynomial has a root, right? That's what algebraically closed means. So you can factor out that root. Then what remains is another polynomial of degree 1 less. Yeah, so that will also have a root and so on. But it may happen that all the roots are same, right? So you can't say it has more than one. It certainly has to have more than one eigenvalue. You can only say it has at least one eigenvalue. But it's always a product of linear factors. Okay, so now for a linear map, we can say phi is diagonalizable. A linear operator P on V is called diagonalizable if the matrix associated to it is diagonalizable, yeah, which means the matrix of phi with respect to some basis is diagonalizable. But we know that if we can, that pretty much means that if we can find a basis such that the matrix of phi with respect basis of V, such that the matrix of phi with respect to V is diagonal, yeah. So this will be our definition, and okay. So and similarly, triangulable is and maybe the other thing will be a consequence. Yeah. So maybe let's split it that way. It's going on. Sorry, so something has created a problem. So I'll have to restart my OneNote. Yeah. Yeah. So, oh, I have to share as well. God. Share screen. Hello, are you with me? Yes, sir, we can hear you. Okay. Okay. Yeah, so it started. I don't know why it says started. Okay. And now you can see the screen as well, I hope. Yes. Okay, good. Okay, then let's try to do this. Yeah. So and similarly, we will say that phi is triangulable if the matrix of V with respect to a basis is upper triangular. Okay, so this is the definition of this. Now, the first observation I wanted to say is that phi is yeah, so yeah, so maybe the way to write it is A is similar to a diagonal respectively upper triangular matrix if A meaning a matrix A n cross n matrix if and only if phi A, the map from Fn to Fn is diagonalizable the phi A is this natural map, yeah, which sends V to AV. Column vector V to AV is diagonalizable, respectively triangulable. Okay, so this is basically clear, right? Because so maybe the argument will be, suppose so maybe I'll do both directions simultaneously. So uh, A is, so it's enough to do one of them, yeah, either diagonalizable or triangulable. I mean, the argument is same. So A is diagonalizable is similar to a diagonal matrix. It is similar to a diagonal matrix if and only if P inverse AP is diagonal for some P. Yeah. Then what is the basis you have to take for Fn, which will for with respect to which um, this will become a diagonal matrix? Any guesses? Which basis you'll have to take? Let B be the basis. Yeah. So tell me. So you have to do a change of basis matrix. You'll have to apply a change of basis. Um, um, Apply a change of basis matrix to the, so phi A, the matrix of phi A is A with respect to which basis? That we know, right? For which basis is the matrix of phi A? Anyone? Standard basis, right? So we know that for standard basis, the matrix is going to be A. So now we want to change the basis, yeah, so that it becomes P inverse AP, right? So so P is the change of basis matrix, and then if so you take the B to be the basis consisting of this PE1 to PEN. Yeah, you apply P to these the standard basis vectors. Yeah, then you get then of course this is a basis, and the matrix of phi with respect to B is precisely with respect to this basis is precisely P inverse AP. Okay. So this is something which you can check. Okay. Which is type. And conversely, if this proves both direction, yeah, is diagonal if and only if there exists this, and if phi a is diagonalizable, that means you have a basis like this, yeah. So you just conversely, if you have a basis like this, then you just make the matrix P by taking these as columns of that matrix, yeah. So, if PA is diagonal, if the matrix of phi with matrix of phi with respect to v1 to vn is diagonal, and then take p equals this matrix. So v1 is a column vector of length n, v2 is a column. So you just consider this matrix whose columns are v1 to vn. Then we'll have again that p inverse ap is diagonal. Yeah, so this proves both direction that um, that is diagonalizable if and only if A is similar to. And similarly, you replace the word diagonal by triangulable or upper triangular, and you get the result for upper triangle. Is this okay? Yeah, makes sense, everyone? Okay. So now we want a criteria for something to linear operator to become upper triangulable or diagonal. Yeah. So first maybe upper triangular. So the first result is that if the characteristic polynomial of a matrix is product of linear factors, then it is similar to an upper triangular matrix. Yeah. So we know that. Sometimes we know that our linear operator may not have any eigenvalue. Yeah. For instance, we saw that rotation matrix. So of course, then that matrix, rotation matrix, you can't make it similar to a upper triangular matrix. But as long as the eigenvalues as long as the characteristic polynomial is product of linear factors, then you can make the matrix similar to upper triangular matrix. So in particular, if the base field is algebraically closed field, like complex numbers, then you can always make a matrix similar to a upper triangular matrix. Yeah? And if you want to write it in terms of linear map, by the above observation, you can say that equivalently given a linear map phi on an n-dimensional vector space, such that its characteristic polynomial. So if you are given a linear map phi which has the property that its characteristic polynomial is product of linear factors, then you can find a basis of V such that the matrix of phi is upper triangular. Or I could have written, since I wrote that definition, I could have written that then phi is upper triangulable. Yeah. Is that okay? Is triangulable? Yeah. So first thing is that the two statements are equivalent. So we only have to prove one of them. Yeah. So we'll prove the matrix version. Yeah. So that A be a square matrix and n by n matrix, n by n matrix, such that characteristic polynomial of A is product of linear factors. Okay, so So once you have that the characteristic polynomial is product of linear factors, that means it has at least one eigenvalue. Yeah, so maybe to fix notation, let phi a be the associated linear map. Yeah, so that we can use them interchangeably, a and phi a. Yeah, so is the associated linear map Fn to Fn, sending V to AV. Okay. So let lambda be the eigenvalue of phi and V1 be a lambda eigenvector of phi a. Okay. So of course, any non-zero vector, we can extend it to a basis of V, right? So V here is Fn, V equals Fn in this case. So we can extend it to a basis of V and call it W1 to Wn minus 1. Then what is the matrix of phi a with respect to V1? Then so it has to have this form, right? So V1 is basically lambda multiple of V1. So the first column has to be lambda 0, 0, 0, 0, 0. Yeah. And then the rest, we don't know what it looks like. So there will be something in the first row, and then you'll get a matrix B, which is a square matrix of order order n minus 1. Yeah. And since we have changed the basis from standard basis, we have gone to B1. It is same as saying that there exists a matrix P1 such that P1 inverse AP1 is this matrix lambda star 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 0, 0, 0, where B is n minus 1 cross n minus 1 matrix. Is this fine, everyone? Yeah, so far so good. So now we'll use basically induction on n, the size of n. Now B is an n by 1, n minus 1 cross n minus 1. What can we say about the characteristic polynomial of B? So to use induction, we'll have to show that this smaller matrix also has this property. But what is the characteristic polynomial of B? So so you just have to calculate the determinant of this thing, yeah? T minus lambda, and there will be this something, and here you'll get zeros, and this will be Ti minus B. Yeah, this is how it will look like, determinant of this particular matrix. Right, and what is the determinant of this matrix? This block matrix. T minus lambda characteristic polynomial of B. Yeah, so this determinant is T minus lambda times determinant of this block, right? Because it's an upper triangular matrix. So it's just the determinant of the blocks, yeah, diagonal blocks. So this is determinant of, so this block is just a scalar, so it's just T minus lambda, and this is determinant of Ti minus lambda. So the LHS is characteristic polynomial of B1. Okay. Oh, sorry, the LHS is characteristic polynomial of this P1 inverse AP1, yeah, which is same as A. Characteristic polynomial of A. Sorry, so yeah, this is yeah, so maybe I should write it as, yeah, you're right. So this is characteristic polynomial of AT is characteristic polynomial of P1 inverse AP1 T. This we already saw. And this is precisely, so I've just written the matrix, is determinant of this guy. Yeah. Now it is okay. Yeah. And the second factor is precisely the characteristic polynomial of P. So this is T minus lambda times characteristic polynomial of B. Yeah. So that tells you that, so since left hand side is a product of linear factors, the right hand side must be a product of linear factors as well. Yeah. Hence. Yeah. Is product of linear. Right. So by induction, hypothesis, what can we say? There exists Q of order n minus 1. Sorry. So this is a square matrix of order n minus 1. Yeah. Q of n minus 1 cross n minus 1, non-singular. So non-singular or invertible, such that Q inverse BP, Q inverse BQ is upper triangular. Yeah, this is what the induction hypothesis will give you, right? So now we'll have to combine this information. Yeah. So what do we do? So we'll have to make up another n cross n matrix. Yeah. Let's call this Q. Q. Yeah. So Q1. Let's call this Q1. Okay. And let's make a Q which is n cross n. Yeah. So we want to have Q1. See, we want to have Q1 in this factor. Yeah. So there and here it should be 1. We don't want to do anything there. We want Q1 here, and maybe put zeros here. Yeah. So 0, 0. The 1 and the rest is 0, and here 1, rest is 0. So we take Q to be this. Yeah. And then apply. Yeah, so now maybe this will work. Yeah, so now what happens to Q? So if I do, then let Q be this. Then if we do Q inverse, P inverse, A, P1 inverse A, P1 Q, then we know that this is same as Q inverse, or maybe let's just write what Q. So what is Q inverse? It's a block diagonal matrix. Yeah, so Q inverse is just 1, Q inverse 0, 0. Yeah, so if you multiply these, so Q1 inverse, so if you multiply these two, you'll get identity. Yeah, so this is what Q inverse is. P1 inverse A P1 we know is of this form, so let's just write that one. Yeah, and zeros and B here. Yeah, and then Q is 1 string of zeros, a string of zeros, and Q1 here. So this is a block diagonal matrix, and you are trying to multiply conjugate this matrix by a block diagonal matrix. Then this you can do the calculation. This will come out to be, you multiply this thing by. So here you don't have to do anything. So it will be lambda. Yeah. So lambda, and the strings remain same. So and then this at lambda, yeah. This is, yeah. So this entry may change, but we don't really care about this entry. So it may not be the same stars, yeah. So that is what I was checking, whether this entry change or not. So this entry may change because you are multiplying, but this will be 0. And but this piece is just going to be Q1 inverse B Q1. Okay, because here you have zeros, and the top is also 0. So this piece of the n cross n block is going to be this. So this is some matrix calculation you must have seen earlier. Yeah, And this, of course, we know is so this is upper triangle because this part is upper. I mean, this Q1 inverse B Q1 is upper triangular. Then this becomes upper triangle, which is upper triangle, which is upper triangle. Yeah. Hence, so you just take P to be maybe, hence taking P equals I don't know P1Q. We see that A is similar. Okay. Any questions? So that completes the proof of this thing. Yeah. So in fact, I can tell you. So maybe I'll tell you what this stars is. So this I had done the calculation earlier. So if this is the some is going to be a row vector of length b. Yeah. So let's call this just b instead of twiddle b. Yeah. So by let's keep a dash to say that is vector b. Then this thing will become b transpose q1. Okay, so you can check that it comes out to be this thing. Okay, so you just have to, I mean, you just have to do the multiplication. So you get lambda, and then so you multiply one at a time. I mean, these two matrices, and then whatever you get, you do that, then you'll get. Okay. Okay, so that completes the proof of this thing. So using sort of similar technique, we so or maybe first a corollary. If F is algebraically closed field, then every matrix, every square matrix over F is similar to a to upper triangle. Yeah, maybe I should move to a different panel. Why is it acting so much? I'll have to, it's not behaving properly. Yeah, so let me just reshare this. Now it is. Yeah, so maybe it's a bit too small. Is this still visible a little bit? Yeah, please talk. Yeah, it's otherwise it becomes a dead class. Yeah, is it visible? somewhat, or should I make it slightly bigger?
Yes, sir.
Make it slightly bigger, huh? Okay. Maybe this is better.
Yes, sir.
Yeah. Okay. So next is we can play the same game with diagonal, yeah. But we need what was the condition for a matrix to be diagonalizable? You remember? We discussed one condition last time, yeah. And similarly, a linear map to be a linear and endomorphism to be diagonalizable, yeah. So what was one condition? That it should have a basis consisting of eigenvectors, right? So that of course is a tautological condition, but we want to use characteristic polynomial somehow. Okay. So maybe let me just first state the theorem, and then we will. So let A be a matrix such that the characteristic polynomial CHA be a n cross n matrix such that characteristic polynomial of this has n distinct roots. So as I said, sometimes you may have equal roots, but this has the good property that it has n distinct roots. Okay. So that means in particular, characteristic polynomial is the product of linear factors. So the previous theorem, previous proposition tells you that A is certainly similar to an upper triangular matrix. But if this happens, then A is diagonalizable. A is diagonalizable. And then you can make a same statement for a linear map, yeah, a linear operator on a vector space V. So the characteristic polynomial has n distinct roots, where n is the dimension of the vector space V. Then that linear operator is diagonalizable. So they are more or less the same statement, yeah, because of this proposition which we proved. Where's that? Yeah. So this statement which we proved, that A is a n cross n matrix similar to a diagonal, respectively upper triangular matrix, if and only if A is diagonalizable. Yeah. So this tells us that these two statements are more or less the same. Okay. So can make the same statement for linear operator. So these are equivalent statements for linear operator on n-dimensional vector space. Okay, so basically, so we'll this theorem follows from the following proposition. So the above theorem so maybe I'll not write it. I'll write the proposition, and then we will prove the proposition and then the theorem. Yeah. So what do we? So we saw that one characterization is that if it has a basis of eigenvectors, yeah. So this proposition will tell you that if this happens, then it has a this matrix has the eigenvectors of A form a basis of Fn. Yeah. So maybe I'll this second statement, maybe instead of matrix, I'll state it in terms of linear map. So even the first one I could have stated in terms of linear map, but let's mix so that we get used to both of them. Yeah? So let P be a linear operator on it's losing power. It may need recharging. Let Phi be a linear operator on a finite dimensional, on an n-dimensional vector space. Okay, I don't really care about finite dimensional vector space V. Let V1 to Vm in V be eigenvectors of P with respect to eigenvalues or with eigenvalues. Maybe actually it's not with respect to, but with eigenvalues lambda 1 to lambda m respectively. Okay, and suppose that all these lambda i's are distinct. If lambda 1 to lambda n are distinct, then V1 to Vm, this set is linearly independent. Yeah. So this is our proposition. So before proving the proposition, maybe we see a proof of theorem using this proposition. Yeah, because this is just ideas. Yeah, and this is just what we said. Yeah. So proof of theorem using the proposition, and then we will see a proof of this proposition. Okay, so what is the proof of theorem? So, since CHAT has n distinct roots, let's say, I will say lambda 1 to lambda n. So for each eigenvalue, you'll get an eigenvector. Yeah, so let Vi be a lambda I eigenvector vector of A. Then we are in the setup of the proposition. Yeah. Then by proposition, V1 to Vn is linearly independent. Yeah. But V is n-dimensional, and or rather F, yeah. So is linear, and our A is an n cross n matrix. So our space, our vector space is n-dimensional. Yeah. So linearly independent, and hence a basis of Fn. Yeah, so we are using in the theorem, we are using sort of A, yeah, not so we wrote the version for the matrix rather than the operator. So that's why Fn. Yeah, hence by the result we saw in the earlier class, hence A is similar to a diagonal matrix. So I P inverse AP is type. Can you say what P will be in this case?
Change of basis matrix from standard basis to the ideal vectors basis.
Yeah. So where P is, and so in terms of, so you can say in terms of what is written on this thing. Yeah. What should I put in here? So these VIs are vectors, right, in Fn. So you just have to put this thing. Yeah. So you'll use this matrix essentially. Okay, and you'll get the diagonal matrix. Okay. So this is the change of basis matrix from EI to V1 to Vn. Okay. Is that fine, everyone? So this is the proof of the theorem, assuming the proposition. Now let's just prove the proposition that if we take this thing, so this is also not too difficult. It's just some observation, proof of proposition. Yeah. So, I mean, if it was, I mean, one can think of it one by one. Yeah. So if there was only one vector, there's nothing to prove. Eigenvectors are supposed to be non-zero and so on. Yeah. So it is okay. If there are two vectors, yeah. So if you think about it, say V1, V2. So what we'll have to say that A1, V1. So let's try 2 and then we will go for general. Why does it create this trouble? Good. Yeah. So again, what we have to do is, yeah. So now suppose there are two vectors, V1. So say AV1 plus BV2 is 0. Okay. Then we'll have to argue that A and B both are 0. So what do? You apply this linear map, yeah, and see what happens. So if you apply phi, then what you get? A lambda 1 V1, because so apply phi. Apply, yeah, I've written the proposition in terms of phi. Apply phi. But phi V1 is just lambda 1 V1 and phi V2 is lambda 2 V2. Yeah, so you get V lambda 2 V2 is also 0. Yeah. So now, I mean, and lambda 1 and lambda 2 are distinct, right? So by this, so you can eliminate one of them. Yeah. So for instance, you can multiply this by lambda 1. Lambda 1, take the difference. So the first will, this factor will cancel out and you'll get B times V2 times lambda 1 minus lambda 2 is 0. Yeah. But B, so this tells you, but lambda 1 times lambda 2, lambda 1 minus lambda 2 we know is non-zero. So this will imply that B must be 0. And once B is 0, A must be 0, which implies A is 0. Yeah, so this is for two vectors, you can do this. So in fact, this you can do more generally. Yeah. So, so maybe this was n equals 2 case. N equals 1 is straightforward. So generally what you have, so maybe you use induction on n. Use induction on m rather. That statement was with m, right? Induction on m. So so let's suppose we have a condition that A1 V1 plus AM VM is 0. So we want to prove that it's linearly independent, then we'll have to show that all the AIs are zero. Yeah. So again, you apply. So the idea was to apply phi. Yeah. Apply phi and see what happens. So then we'll get A1 lambda 1 V1 plus AM lambda M VM is zero, right? Because these are all eigenvectors with eigenvalues. Since Vi, since phi Vi is lambda I Vi. And this is what we are using. So again, I want to cancel one of them so that we get a relation among smaller guys, and then we can conclude that that must be zero. Yeah, so you multiply, so you, let's call this star and this double star. Yeah, so what we do is lambda times star, lambda 1 times star minus double star. If we calculate this, then what do we get? So the first term will go away and we'll get lambda 1 minus lambda I times AI, or rather let's say, yeah, maybe I'll just write in terms summation on AI, Vi, and then you sum it. I equals, I mean, you can write 1, 2, but one term will be 0. So let's write it from 2 to n. This is 0. Yeah. So that tells you now the length is shorter. So this must be, but by induction, hypothesis V2 to VM are linearly independent. Yeah. So that tells you that hence each of these coefficients must be 0. Lambda 1 minus lambda I times AI is 0 for all I between 2 to m. But the first factor is non-zero because we are assuming all the lambda is are distinct. Yeah, so this implies AI is 0 for all I between 2 to m. But then A1 also must be 0. Yeah, A1, V1 can't be. So if A1 is non-zero, then left-hand side will also be 0. So this also implies A1 is also 0. So that's it. Okay, so that gives you the proof of this proposition. Okay, everything fine? Yeah. So this is what the proposition looks like. Proof of the proposition looks like. Okay. Okay. So have you heard of Cayley-Hamilton theorem?
Yes.
Yeah. Okay. So next we will prove the Cayley-Hamilton theorem, and that will allow us to define minimal polynomial. So yeah. So maybe we'll take a 15 minutes break, 10 minutes break. Maybe we'll start at 12:10. Yeah. So let's take a 10 minutes break and then we will do it. So I don't want my back to hurt. So let's take a, let me pause recording. Okay. So now let's try to give a proof of Cayley-Hamilton theorem. So Cayley-Hamilton theorem. So first I'll state what this is. So what is the version you know? Cayley-Hamilton theorem. The matrix satisfies characteristic polynomial. Yeah. So that is so let A be a square matrix, or maybe since you know the matrix version, let me write it in terms of linear operator. So let phi be a linear operator, be a linear operator. So it's the same statement, but on a finite dimensional vector space V. Then we can define the characteristic polynomial of V. Let ft be the characteristic polynomial of V. So, but you'll have to choose to define it, we have to fix a basis and then write the matrix of phi with respect to that basis, and then say take the determinant of lambda I minus that matrix. And then we know that it does not depend upon the choice of the basis. Yeah. The characteristic polynomials. Characteristic polynomial of phi. So I'll interchange so that you get comfortable with both the abstract version and the matrix version. Yeah. Then the statement says you can consider f phi. Yeah. So um, so what is f phi? So I'll have to tell you what f phi is. So then f phi is zero. Is what one zero. So let me just elaborate on this last line. So note ft is going to be some polynomial. Yeah. So it's going to look like, and it's a monic polynomial. We saw t power n, a n minus 1, t power n minus 1, where n is the dimension of the vector space A0, as ai's are in the base field F. ai's are in F. Yeah, so this is what ft will look like. Then Fv is this linear map. So Fv is basically, you consider phi power n, which is you compose phi with itself n times. Yeah. So if I write a matrix times n, that of course multiply the matrix with itself many n times. Yeah. So similarly, phi, if I write it as a linear map, it means you compose phi with itself n times. Yeah. Similarly, an minus 1. So an minus 1 is a scalar, right? And is a number, is a element of the field. So if you compose this phi with itself n minus 1 times and then multiply by this, you again get a linear map. Yeah. So it's this linear map and so on. So, and then you can add linear maps. Yeah. So like matrix, if you consider set of all n cross n matrix, it's a ring. You can add them, multiply them, and so on. Yeah, and you can also multiply by the scalar. Similarly, endomorphism of a vector space is a ring. So all this makes sense. Yeah. So A0, and then A0 as such is just a scalar. So you want to think of it as a linear map. Yeah. So you put A0I. Yeah. So then Fe is this. And then you are saying that this endomorphism is the zero endomorphism. That's what this means. Yeah. So if you want to write it in terms of is the this is this yes, so this is a linear operator, is the zero linear operator. So this is a linear operator, is the zero linear operator. Zero operator, linear operator on B. This is what, so maybe this is the elaboration of then Fe is zero. Okay, so this is what Cayley-Hamilton theorem is, which is equivalently, so So since we'll prove the matrix version, I should write down the matrix version as A n plus n matrix and Ft is CHAT, characteristic polynomial of T. Then of course, then I can't write anymore. Yeah. I guess if it gets hot or something, then it becomes a bit. Any idea why it stops working suddenly? Let's see if it works now. Okay, so it looks like I'll have to. It's not allowing me to write. I started writing. Okay, good. Equivalently, A is a n plus n matrix and Ft is this, then Fa is the zero matrix. See. Yeah, this is what the usual version, the matrix version is. Yeah. So let's see. So the key aspect of this. The key trick in this proof is the following. Yeah. So first of all, I mean, so there is a fake proof. Yeah. So maybe it's sort of fake proof. So you know that Fa is what is determinant of Ti minus A. Yeah. So Ft, sorry, not Fa, Ft. That is the characteristic polynomial. So Fa, you can say that is determinant of Ai minus A, which is of course 0 because Ai. So what is wrong with this proof? So the point is, Fa, we are not, I mean, this is a polynomial, right? Though it's written determinant. So I mean, you can't, this is determinant of some matrix. Ti minus A is a matrix and you're trying to do the determinant of this thing. And when you plug A, the capital A, then it doesn't remain a matrix. Yeah, it becomes A minus some A1. I don't know, depending upon what, but if you put entries like this is not at all a matrix, right? The entries of this matrix is a matrix. That doesn't make sense. Yeah. So this is that's why it is not really a proof. Yeah, it's some symbolic manipulation. Yeah. So that is what is wrong with this. Yeah. So we'll have to actually do some work. Yeah. So it's not trivial. Yeah. So let's see a proof. So if you plug in A and then try to calculate the determinant, you have lost the matrix. Yeah. So what do you do? So the trick is this. Yeah. So this determinant of T of a matrix. There is a way to calculate it. Yeah. So if I give you if I have Ti Ti minus A, yeah, and I want to calculate the determinant of this thing. Yeah. So how do you calculate the determinant of this thing? With a matrix, so you can use a matrix to calculate the determinant of this thing. Yeah. So what you do is you multiply by the adjoint of this matrix. So you know what adjoint of the matrix is? So this becomes determinant of ti minus a times, what do you get? Times the identity. Yeah, so this is, you know what the adjoint is, right? So, okay. So, I mean, T is just a number. So think about it as a number. So it is some matrix. So this is determinant of Ti minus A and so on. The diagonal is a diagonal matrix with entries this. And this is 0. Yeah, so it is basically determinant of Ti minus A times. So everyone knows what, okay, there is some message. Yeah, so that is about open board. So I'll tell you after the class, yeah, Anarka. But um, uh, so does everyone know what is the adjoint of a matrix is? Yeah, so I mean at A11 you will write down the minors where you delete the first column and the first row and write down the determinant of the remaining n minus 1 cross n minus 1 matrix. At A12 you remove the first row and the second column, compute the determinant and multiply by minus 1 and so on. Yeah, so that is the adjoint matrix. So that is what I'm saying. So we have this property that adjoint, when we multiply by the adjoint of this matrix to T, we get this. Okay. So now, so what we know is that yeah. So yeah, so this is just ft times I. Yeah. So this is what we get. Right. So let's try to expand this. Yeah. And maybe we'll call this matrix as H. Yeah. Or rather HT. So it's also depending on T. So it's a matrix which depends on T. Yeah. And Ti minus okay, anyway, that is a explicit matrix. So we have this formula. So let's try to expand this, what we get in terms of, so what is HT? HT is a is again a matrix with entries in T. Yeah, and so let's try to write this down more comfortably. Ti minus A is ft is this polynomial, yeah. Where is this? Is some polynomial like this. So let's just write it that way. So this is t power n plus a n minus 1 t power n minus 1 plus and then I. Yeah, so one should put I everywhere. And so on. A n minus sorry, not n, a1 a1 ti and then a0i. Yeah, so this is what right hand side look like, and left hand side is this. Yeah, so again, left hand side you can think of it as a polynomial in T with coefficients in the as matrix. Yeah, so left hand side. So maybe HT in particular. So let's write HT as a polynomial in T with coefficients. So note HT is going to look like something like this. HT is going to be some H. Yeah, so and hn minus 1 t power n minus 1 plus h naught h1 t plus h naught. Yeah, I've written n minus 1 because the product has to be a degree n polynomial with coefficient in the matrix. Yeah, so it can't go beyond n minus 1. All the other coefficient must be 0 because ht times lambda t minus a must be degree n. Yeah, so and this ti minus a is degree 1, so you can't go beyond this. Yeah, so note ht is this for some matrices h naught to hn minus 1 of size n cross n. Okay. So now let's try to expand this and try to get some identity. Yeah. So unfortunately, I have to do some calculation because the abstraction is not there. Yeah. So I mean, if you knew some this modules over rings, etc., that description and what it means to be a Rx module and so on, then this is the only trick. The first adjoint it gives you determine. That's the only trick. This is sort of gets into the abstraction part. Yeah, so let's try to calculate this. So if you multiply this ht so if we expand this star and then equate the coefficient of t power n and t power n minus 1 and so on. Yeah. So if we do that, then what do we get? So if we do that, then let's look at the constant term. Yeah. So what will you get as the constant term? So left hand side is h. The constant term will be minus a h naught. Yeah. Right. So then you'll get that minus a h naught on the left hand side should be same as a naught I. Yeah. This is the identity we'll get. Right. And then the term coefficient of t. So what will you get if you look at the coefficient of t? So right hand side is just a1i. And what will be the left hand side? So h1 minus h1 times a and then plus h naught. Yeah, so this is h naught minus h1 times a. Yeah, so but we'll have to do it in the right order. So minus h1a is what I'll do. So I hope it doesn't matter. So here I've written it in the reverse order. So we should just fix one order, whether we are post multiplying or pre-multiplying, it doesn't matter. So let's just stick to what we have written. Yeah. So h naught e. And here it will be h naught h minus h1 h1. Is this okay, guys? And then you keep on going. So this is the so these are coefficients. So what here we are doing is equating coefficients of t power I in star. Yeah. So left hand side and right hand side we are writing that. So we get if you keep on doing it, then you'll get h n minus 1, n minus 2, maybe let's write hn minus 2 minus hn minus 1 a is, so this is the coefficient of t power n minus 1. Yeah, so an minus 1 I. And then for t power n, we'll get that there is only hn minus 1 times I. Yeah, so which is hn minus 1. hn minus 1 is equal to an minus 1. an minus 1 times. So these are the identities we get. Yeah. So remember, what do we have to prove? We'll have to prove that if we plug in A here in F, then we get the zero operator. Yeah. So that means we want to prove that A power n plus an minus 1, A power n minus 1, and so on, A1, A plus A0 is the zero matrix. Yeah. So what do? We multiply this one by n minus 1. Yeah. Sorry, so I think this should be this is an minus 1. An is 1. Yeah. So this should be, so that's why I thought there's something wrong. An is a monic polynomial. Yeah. So hn minus 1 is just right, guys. Hn minus 1 times. So if I'm looking at the coefficient of t power n, then I have to multiply hn minus 1 with identity. Yeah, that is the only thing which will give us the coefficient of t power n, which is hn minus 1. And on the right hand side, the coefficient of t power n is identity. So we get this identity. So now what I do is multiply this by a power n, this equation. This by a power n minus 1. Yeah. And this by a1. And this nothing. And then add them together. Yeah. And let's see what we get. So if I add them together, and then on the left hand side we get yeah.
Can we multiply the last one by a power n minus 1, the previous one by a power n minus 2, and so on?
And how will that help?
In the left hand side, everything would get cancelled. So you have a 0, and on the right hand side, you have the.
Yeah, so it is cancelling, right? It is, so that's what I was hoping it will cancel. It is cancelling, right? Yeah, even if we multiply this way, it is okay. It is, yeah, so the left hand side is 0, yeah? Because it's becoming this, so it's hn minus and add, yeah? So multiply with this and add. So this is hn minus 1 times a power n. And in the previous term, you get minus hn minus 1 times a power n again. And plus hn minus 2 times a power n minus 1, which will get cancelled with the previous term, and so on. So h1a will get cancelled with the next third in the third row, and h0a will get cancelled with the first row. Yeah. So left hand side is 0 and right hand side is precisely f of a. Right? 0, which is equal to the right hand side. But right hand side is precisely f of a. Is this okay? Yeah, this is what you were suggesting maybe, yeah? So you don't have to multiply by a power n minus 1, but a power n itself. The last row by a power n, the second last row by a power n minus 1 and so on up to the so the first row you multiply by a power 0, second by a power 1 and so on and add them. Yeah, so this becomes telescoping sequence. Yeah, so it cancel the terms get cancelled out. Hn minus 1 times a power n gets cancelled out with this one and so on. Yeah, so this is so you get that this is 0. Yeah, so that proves what we wanted to show, that FA is indeed the zero matrix. Okay, so that completes the proof of Cayley-Hamilton theorem. Any questions?
Sir,
Yes.
you express once more the equations that you found.
How I got these equations? Okay, yeah, sure. So let's look at this once again. So this what happened. So I maybe jumped one step. Yeah. So let's look at this star. Yeah. So let me write this star again. Star implies this. So if you multiply this through, what you will get is um, so hn minus 1 times t power n minus 1, t power n. So I'm just multiplying this ht with ti minus a. Yeah. So I'll get hn minus 1 t power n plus what is the coefficient of t power n minus 1? It will be hn minus 2 minus hn minus 1 times a. Yeah, hn minus 1 times a times t power n minus 1 and so on, plus you'll have to go to till h naught minus h1a times t. So just multiply this expression for ht with ti minus a, and the last term will be last term will be minus negative, no? Negative h naught a. Oh, sorry, t is missing here. Minus h naught a. Yeah. So star implies this is same as t power n. Maybe I'll write the matrix in front so that it's similar. an minus 1 I t power n minus 1 plus so on. a1 I t plus a0 I. Yeah, so this is how you can write that star. Yeah, and then you equate the coefficient of t power I for various i's. Yeah. So now equating the coefficient of t power I, you get these identities. Yeah. So h power n minus h sub n minus 1 is I. H sub n minus 2 minus h sub n minus 1 times a is the coefficient of t power n minus 1 on the left, and on the right is an minus 1 times I. So these are the one in the bracket is precisely the identity. Yeah. Is that okay now? Yeah. Yeah. Okay. Good. Any other questions? Okay. So let me start. So maybe we'll just define minimal polynomial and we'll prove some properties next time. Yeah. So since I promised the definition. So definition. Let A be a n cross n matrix over a field F. So again, one can define it for a linear map, but okay, first matrix. Harmonic polynomial with monic polynomial, let's give it a name, P x is with coefficients in F, with coefficients in F is said to be the minimal polynomial of A over F. So somehow the F is important as well, yeah? Minimal polynomial of A over F. If PA, when you plug in A, it should be 0, okay? And P is the smallest degree polynomial with this property. And Px is the smallest and degree Px is this so Px is the least degree polynomial with this property. Is the least degree monic polynomial this property. Right. Okay. So first of all, there is a polynomial, monic polynomial, such that PA is 0, right? What is that polynomial? The characteristic polynomial, yeah. So there is always a monic polynomial which A satisfy. So now you just have to look for, so you look for the smaller degree polynomial, yeah. So in the what we have proved, the upshot of this is that Cayley-Hamilton theorem implies that minimal polynomial exists. Implies minimal polynomial of a matrix exists. So of course, you can look at all polynomials, all monic polynomials which satisfy. Look at the minimal degree. Yeah, so there has to be something of the least degree. Right? So since the set is non-empty, you can find some least degree guy, and that will. So there exists one. In fact, next time we will show that it is unique. Okay. So there won't be more than one. Okay. And we will also show that minimal polynomial divides the characteristic polynomial. This is the first thing we'll do next. Okay. So let's stop here, and we'll meet on Wednesday. So on Wednesday we will meet around 11:15. Yeah.